Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. Welcome to today's physics class. Today, the topic of our discussion is chapter 7, Waves and Sounds. Today is the first class on this chapter. And the objectives of today's lesson are: we will understand the properties of simple harmonic motion, in short, that is called SHM. At first, we will provide the definition, and then we will learn the advanced or acceptable definition of simple harmonic motion. Then we will go through the examples of it. Then we will understand the Hooke's law and we'll demonstrate it using a simulation. And we will also understand how Hooke's law also works in simple harmonic motion to describe its motion. And then we will understand the dependence of time period in simple pendulum and in mass spring oscillator. At first, when we define simple harmonic motion, we recall the concept from chapter 2 that is also called vibratory or oscillatory motion, and its definition is: it is a kind of periodic motion in which a body travels half time period in definite direction and another half time period in opposite direction. That means the object travels a particular point along its path after a regular interval of time, and it travels half time period in definite direction and another half time period in opposite direction. Examples are the motion of simple pendulum, the motion of mass spring oscillator, the motion of vibrating tuning fork. Now we see the examples. This is the animation of a simple pendulum. Now that is at resting phase or equilibrium position. If you make some angle with the equilibrium position, then release it, we will see the simple pendulum is moving rightward and leftward, that is swinging to the right and then to the left. And if you see, in case of a mass spring oscillator, that there are two springs. If we attach two masses with these two springs and then release them, what will happen? These two load masses are now moving downward and upward. They are moving downward for half time period and then moving upward for another half time period. And in case of a wave on a string, here is a rope. This rope has no end long enough, that is connected with the oscillator that produces oscillation on the string. Then we will see waves are produced on the rope or string. Here we see each particle is moving upward for a half time period and moving downward for another half time period. So that is why we say the wave on a string, the mass spring oscillator, and simple pendulum all are example of simple harmonic motion. Now we will move into the most acceptable definition of simple harmonic motion. That is the advanced definition of simple harmonic motion, but most appropriate, you should learn it. The most acceptable definition of simple harmonic motion is: it is a kind of periodic motion where the restoring force on the moving object is directly proportional to the opposite of the object's displacement. So here we are saying that a restoring force acts on the moving object. So we see simple harmonic motions are such type of motion where a restoring force will be produced on moving objects that will lead the moving object towards the equilibrium position, and the amount of restoring force will be proportional to the displacement and will be opposite to the displacement. So we will understand this definition on the practical examples. For example, we have taken the simple pendulum. When we take the simple pendulum and release it, we see the simple pendulum is swinging left and right. Now we see the simple pendulum has a maximum amount of displacement now towards the right from the equilibrium position, and now it has maximum displacement from the equilibrium position to the left. The restoring force is acting on the object to rightward, that is leading the object towards the equilibrium position. So the restoring force is acting on it to get it on the equilibrium point. But what happens when this restoring force acts? It has acceleration. As a result, its velocity increases, but due to inertia of motion, it surpasses the equilibrium point and also travels some more path. As a result, it goes to the another extreme, and then so as a result, the opposite restoring force acts on it. So if we see, if there is displacement towards the left side, the restoring force will act towards the right side, and if there is displacement towards the right side, the restoring force will act to the left side, and the amount of restoring force is proportional to the displacement. If the displacement becomes larger, the restoring force will be larger proportionally. And from the definition we say that the restoring force on moving object is proportional and opposite of displacement. Here x is called the displacement, and minus sign indicates the opposite nature of the force. So the force F will be proportional to the displacement and will be opposite to the displacement. So the opposite is indicated by the minus sign present in the equation. And now we can write equal sign if we provide a constant k. So then the equation becomes F equal minus kx. Now we will understand that simple harmonic motion uses the same formula of Hooke's law. As we have used the formula F equal minus kx in simple harmonic motion, the Hooke's law also employs the same mathematical formula F equal minus kx. At first we understand what is called Hooke's law. Hooke's law is also called law of elasticity, and Hooke's law says that the strain or deformation takes place in a solid is proportional to the applied stress or force within the elastic limit of the solid. That means if we apply force or stress on a solid material, it will cause deformation or strain on the solid, and the amount of deformation is proportional to the amount of applied force within a elastic limit. That means this relation of proportionality works until an elastic limit. If the amount of applied force exceeds the elastic limit, the formula will not work. Stress is proportional to strain or deformation. If we indicate the stress as force F, and if we indicate the strain or deformation by displacement x, we can write F proportional x. But now from that we can write F equal minus kx. If we consider the restoring force acting on the solid object, now the restoring force F will be equal to the minus kx. Here minus sign indicates that the restoring force acts at the opposite direction of the displacement x, and here k is the constant of proportionality, that is called the spring constant. Now we will observe a figure. In this figure we have a unstressed spring. There is no mass loaded on it, but if we apply a dead load at the end of the spring, then it will cause a force downward, and as the downward force is acting on it, it will also cause a displacement x. Now what will happen if we make the force double? If we make the force double, then the displacement will also become double. So the elongation will also become twice x if the force is twice F. Now we will demonstrate the Hooke's law using a simulation. Here we see if we apply force on the spring, for example, we are applying now 30 newtons of force. This orange colored force is the applied force. So this applied force has also produced a reaction force inside the spring. So the spring has produced a restoring force that is indicated by the blue colored 30 Newton force. So we have applied 30 Newton force, orange colored, and as a result the spring has also produced restoring force 30 Newton, blue colored, and we see there is a displacement of 30 centimeter. Now if we apply 60 newtons of force, we see the amount of restoring force is also 60 newton and the displacement is 60 centimeters. So here we see the displacement has taken place towards the right direction, but the restoring force of the spring is acting on the left direction. And if we increase the amount of displacement, the amount of restoring force increases proportionally to the opposite direction. This is actually the statement stated in the Hooke's law. Now we will understand the dependence of time period in a mass spring oscillator. We know that in case of mass spring oscillator, the time period T depends on the dead mass loaded at the end of the spring and the spring constant K. At first we define what is called time period. Time period is the amount of time required by a object having simple harmonic motion to complete one oscillation. We write T equals 2 pi root over m by k. That means time period T is proportional to the square root of mass, and that is inversely proportional to the square root of spring constant K. That means if we increase the mass of the dead load at the end of the spring, the time period will increase, and if the spring stiffness is increased, that means if the spring constant is increased, the time period will decrease. Let's see this phenomenon using a simulation. Here we see the simulation of a mass spring oscillator. This mass spring has now no load added to it. And now there is the equilibrium position of the dead mass loaded on the spring. If we make some slight change of the dead load from the equilibrium position, then we will see the object is moving upward and downward. And half time period in a particular direction and another half time period in opposite direction. And we say the restoring force, when the object is at top, then the restoring force now acting downward, and when the object is at the downward position, when there is downward displacement, the restoring force acts upward. And what will happen if we increase the mass? Here we have a particular amount of time period, like and now if we increase the mass, so we are seeing that if we have increased amount of mass, there is increased amount of time period. And now what will happen if we increase the spring constant K? If we increase the spring constant K, the time period becomes shorter. It takes less amount of time. That is why we have said that if there is increased mass, there is increased time period, and if there is increased spring constant, there is a decreased time period. And that is also true reversibly. If there is decreased mass, there is decreased time period. If the spring constant is decreased, the time period will increase. And now we'll understand how the time period depends on the gravitational acceleration and length of the simple pendulum in a simple pendulum. We know from the formula T equal to pi root over L by G. That means time period is proportional to the square root of length of the simple pendulum, and a time period is also inversely proportional to the square root of gravitational acceleration. That means if there is increased length, there is increased time period, and if there is increased G, there is decreased time period. We take two simple pendulum. Number one has shorter length, and number two has a larger length. We release them from the same angle, 40 degree, and then release them. We see the number one pendulum, which has shorter length of pendulum L, and that has shorter time period, and number two that has larger length and that has a higher time period. So if you increase the length, the time period will also increase. And now what will happen if we increase the gravity? In case of Earth, the acceleration due to gravity is 9.8. It takes a particular amount of time. For example, if we take a period timer, we can find the time period. Time period is 1.731 seconds. But now if we increase the gravity, for example, if we take the gravity of Jupiter, 24.79, almost 2.5 times greater than the gravity of Earth, then we will see there is a significant reduction in the time period. Now the time period is only about 1 second. So we have increased the gravity. Now the time period has shortened. That is why we're saying that if there is increased length of the pendulum, there is increased time period. If there is increased gravity, there is decreased time period. And reversibly, if the length is reduced, the time period will be also reduced. If the gravitational acceleration is decreased, the time period will increase. So at the end of today's class, what we have learned, let's revise. We have understood the properties of simple harmonic motion. We have provided the definition. Now we know the advanced acceptable definition of simple harmonic motion, and as an example we can say the motion of simple pendulum or mass spring oscillator. And we have demonstrated the Hooke's law, and we have understood how the mathematical formula used in Hooke's law is also applicable for the motion of simple harmonic motion. And we have also discussed the dependence of time period in pendulum. We know that in a simple pendulum, the time period increases with increased length, and the time period increases with decreased gravity. And in mass spring oscillator, the time period increases with increased mass, and the time period increases with decreased spring constant. আজকের মতো ক্লাস এখানেই শেষ। সবাই ভালো থেকো ইনশাআল্লাহ। সুবহানাকা আল্লাহুম্মা ওয়া বিহামদিকা আশহাদু আল্লা ইলাহা ইল্লা আনতা আস্তাগফিরুকা ওয়া আতুবু ইলাইক। আসসালামু আলাইকুম ওয়া রাহমাতুল্লাহি ওয়া বারাকাতুহু।